Alright guys, so hello and welcome to this video tutorial on RC Hibbeler's Engineering Mechanics Statics textbook. So we have this problem from chapter 3 here, which is asking us to determine the resultant force and specify where it acts on the beam measured from A. And we have this diagram here. We've got three different distributed loads acting on the beam, right? I've kind of recreated this diagram here, and where I'd probably start with this problem is, first of all, distributed loads like these can be converted, in a sense, into point loads. And once we do that, this problem starts to become much easier to work with. Let's go ahead and do that then. So we can convert this 6 kilonewton per meter load into a point load on our diagram down here. Since it's 6 kilonewtons per meter and it acts over 1.5 meters, kind of by inspection, we know that we have a point load of 9 kilonewtons acting down to the left of A. Okay, so let's just add that to our diagram in the bottom left here. And just to be extra clear, I've added that this point load is acting 0.75 meters from A. Let's do the same for our 9 kilonewton per meter load and our 3 kilonewton per meter load here. So for our 9 kilonewton per meter load, we note that this acts over a 3 meter span. And so it must, if we're to convert it to a point load, we note that it would be 9 times 3, 27 kilonewtons of force. And for our 3 kilonewton per meter loading over here, that acts over a span of 1.5 meters. And so it would have a 4.5 kilonewton force. So we've converted our distributed loads to point loads here. Now, here we can seemingly work out the magnitude of the resultant force by inspection, right? We can say that the resultant force of these three forces, or at least its magnitude, is going to be 27 plus 9 plus 4.5, which I happen to know is equal to 40.5 kilonewtons. Okay, so that is our result, or at least the magnitude of our resultant force here. So now we're seemingly interested in its position, right? If you were to kind of take these three forces, the 9, the 27, the 4.5, add them all together to give a resultant force, where would that resultant force seemingly be placed on our beam, right? I'm going to estimate it's somewhere here, just for the sake of adding it to our diagram here. Now, the resultant force is, like I say, the sum of this force, and this force. When you add them together, it gives this force, it gives the resultant force. We could say then, surely, that the sum of the moments that are produced from these forces is equal to the moment produced by our resultant force. Okay. Let's describe the distance from A. So we're looking for the distance measured from A here. Let's describe that distance as x. And we could then say that the moment produced by the resultant force is equal to x Fr. I'm just going to call it 40.5. Okay, so 40.5x. That's the moment produced by the resultant force. The moment produced by the three constituent forces is going to be minus 0.75 times 9 plus 1.5 times 27 plus 3.75 times 4.5. I'm going to decimalize our right-hand side here by just whacking it into a calculator real quick. So our right-hand side is equal to 50.625. Now we can divide both sides by this 40.5 coefficient to give x. Put that in our calculator, we find that x is equal to 1.25 meters. So this is part of our solution, and this is also part of our solution, so we can box them up. And that's it. If you have any questions or comments about that problem, please feel free to leave them down in the comment section down below. Otherwise, thank you very much for watching.